The goal of this part of the lecture is to see how these layers are combined to construct useful networks. So let's say that we want to construct a network, kind of this Densenet network, in which you have an input image and then you apply multiple operations, and you see you have this convolution, then a dense block. The dense block, the structure is quite fixed, and then you do another convolution, another pooling, and you repeat the dense block, convolution, pooling, repeat, and then pooling, and the output is the goal is to predict the class of the object in the input. So let's see how this can be done in Keras. Here I'm using these two web pages. So this one is the one that gives the code, and this one, Densenet, you see it is such a useful network. It has got into Keras as part of the standard library. So actually you can import Densenet directly from the Keras applications library, and then some image utilities. So this person here has created this network. Our goal is not to go into every detail of the code, but just to understand how these layers are concatenated. The first one is this input. So the input, typically all the networks, they start with an input layer that somehow adapt the tensor in the tensor that we are in which we have, of the mini batch in which we have all the images adapted to the network. This adaptation is just to make the network aware of the sizes of the input images and the number of images in the mini batch. Okay, so then you could describe, construct inside all these networks, so all these layers, you see how they go. So you do zero padding with this size. So you have an image input, you do zero padding, and you call it X. So the first one is the one coming from the input. So this image input is the one coming from the input, and then you go through a zero padding, nothing to learn here, and you get X. And then you do a convolution 2D with this number of channels, and you would have to go into the documentation. This is the number of kernels, size of the kernels, the strides, whether to put a bias or not, and you can put names to the layers, and you apply it to the previous layer. And the previous layer, the output of the previous layer is X, and you call it X again. This is just a convenient way of applying these things. Then you do a batch normalization, so you do batch normalization with some epsilon, you put a name, apply it on X and keep it in X. Then you go through a ReLU, through this layer activation, and then zero padding again, max pooling in 2 dimensions, and then you go into the Densenet blocks. So it has 2 kind of blocks. One is called dense block, the other one is called transition block. You would have to go into the documentation of Keras to see what is the architecture, internal architecture of these 2 layers, and you give names, and then batch normalization, and then depending on what you want to do, you can include top. Top is the last layers that will do different kind of tasks. So their task may be to classify into 2 categories, or it can be to classify into many categories, so horse being one of them, or whatever. So for instance, let's say that you have 1,000 connected, so clear top, so the last thing will be average pooling, and then doing a dense classification into this fully connected 1,000, because you have 1,000 labels in the output. And then let's say that you don't want to classify, and then just making a pooling is good, so average or max pooling. And then you can, for instance, also use a previously trained Densenet. So you can so these Densenet layers, so which are the weights that you put, and then depending on the configuration of the blocks, you take a more complex or a less complex Densenet train network. So first, let's say that if you want to use the weights trained already for ImageNet, then you get this file from this path, and then once you have the weights, you put the weights here. So now you have the weights. So just the weights path. So you do model, and model is one of these Densenets. Load weights this weights path. Or if you don't give weights, but you give something, so some file, you load from that something, from that file. And then creating the Densenet would be you create your base model. So the base model is just what we did here. So this is our base model. And then you take the output of the base model and you go through an average pooling, some Densenet, dense layer, an activation, dropout, and then you make your predictions into 100 classes, because you have 100 classes for that, and you create your model, and then what you do is you compile your model with respect to this loss function, this optimizer, and these metrics of how good the training is going. So these are monitors on the progression of the network, while the network is trying to minimize this loss. So this would be just an example how layers are concatenated one after the other to produce a useful output, and this concatenation can be very, very, very creative. This creativity helps to have an architecture that somehow is better suited for solving some particular kind of problems.